Hello everyone. We'll talk today about sequence and series, especially the inference series and inference sequences and how to test them. What I mean here by sequences, if we have these parentheses and we have some AN, which is a general term, describes a sequence or this pattern of numbers, or if we have the sum or the addition of all these terms starting from a specific point up to infinity, then we need to test these series. Test it means we need to figure out if these sequence or series converge to a specific value or it's not converging to anything, it's just exploded up to infinity and then we call this divergent. So let's begin. From the beginning, let's define what this sequence means. So sequence, it's an ordered list of numbers with a specific pattern. So for example, we can imagine if we have some set of numbers, and this set of numbers, it's just 1, 2, 3, 4, 5, up to infinity. It's infinite terms. And this set of numbers can be described as some general term and all the list numbers obeying this general term. So if we can see here, it's all of them are just obeying this is the n number, and n is always this positive integer. So also we can think about this as a function, which is this an. This function has some input with n numbers, which get some values 1, 2, 3 up to infinity, and then you will get this set of numbers, and this set of numbers we call this as my sequence. Generally, this n, or if we are speaking about something more general, if we are speaking about, for example, the sine n, the set of numbers will be sine 1, sine 2, up to sine infinity. Again, whatever inside this parentheses, this is our general term. Or we can call this as nth term, as this is a term number n. And generally, any one of these values is called term. So it's a sequence or pattern of these terms, and n is the index of this terms. So this one is a1. We can imagine that right now. So this is the first one. This is a2, and then a3, and this is a at infinity, which is the last term in the set. If we think about how we can express the sequence as a mathematical formula, we can express about this in two forms. One of them is the explicit formula, as we did before, like we have this nth term or general term between these parentheses here, which is n, or we can define this as 1 over n squared, something like this. Or the other way, we can describe this by recurrence relation. What I mean by recurrence relation, there is some relation that already relate the nth term and the term before or the term after. So I can describe something an actually equal an minus 1 over n. So I'm assuming every term will be equal to the previous term divided by the value of this index right now. And then also we can formulate or compose this kind of sequence or this ordered set of numbers. So for example, if we have this explicit formula an equal 1 over n, just for simplicity, we are starting from n equal 1 up to n approach infinity. So this will be 1 over 1, 1 over 2, 1 over 3, passing through any r or any n, up to one last one, 1 over infinity, which is 0. Another one, we can express also an as this n plus 2 over root n, and then we know the numbers will take values from n equal to 1 up to n to infinity, and then also the sequence or the set of numbers can be rewritten as this is 1 plus 2 over square root of 1, and then 2 plus 2 over square root of 2, and then 3 plus 2 over square root of 3, and then we'll end up with, to get the value at infinity, I need to get this limit when n approaching infinity of this n plus 2 over square root of n. For simplicity, these numbers can be rewritten as, again, like this is 3 over square root of 1, this is 4 over square root of 2, and then 5 over square root of 3. This limit at infinity, if we trying to describe this will give us infinity. So this is the sequence of this general term an. Or the other way, if we need to describe this as, or it's already described as a recurrence relation. So this recurrence relation will do nothing, but we can substitute, like given the first term a1 equal to 1. So I can start from a2, which is the second term, will be equal a1 plus n right now, which is 2. I know this will be 3. And then if I need to get a3, this will be equal, again from the same equation, which is this recurrence relation. This will be a2 plus 3, which will be 6. For example, again, for one more time, the a4 at n equal 4, this will be a3 plus 4. This will be 10. So if I need to rewrite this as a sequence, this will be 1, 3, 6, 10. I'm going this way. This is also as a sequence described by the recurrence relation, which is formulated using this equation. So right now we can understand how this formula can be rewritten. So if I need to test the sequence. Test the sequence, it means if the last term in the sequence will converge or will approach some value rather than infinity, or this sequence will end up at infinity. If the last term, which can like talk about this mathematically and describe this as this mathematical formula, if the limit of an when n tends to infinity, this limit will approach number, not infinity, so then we are calling this one is convergence. Otherwise, it means if the limit itself when n approaching infinity of an, this will go to infinity or undefined. So in this case, we are calling this limit here. So sorry, if it's going infinity, then we are calling this sequence as a divergent sequence. So just you are seeking what the final value in this sequence will be. If it's finite value, whatever this finite value, it will be convergent. If it's infinite value, positive or negative, then this sequence will be divergent. Let's see this simply on these two examples. It's required to test the following sequences, and if the nth term is given by an equal ln n plus 2 divided by n squared minus 3, and the other one 2 power n plus 3 power n divided by 4 power n. Before going into the limits, as it's the problem, instead of testing the sequence, it will be a limit problem. So just remind ourselves with some helpful tips in the limits. If we have a polynomial divided by polynomial, and the polynomial in the numerator here, this quotient function, if we have the greatest power in the numerator is p, and the greatest power in the denominator is m, so we will end up with three cases. Either p greater than m, so the degree or the power of the numerator is greater than the power of the denominator, and then this limit will approach infinity, assuming a and b are positive numbers. If one of them is negative number, or like both of them are opposite signs, it will be negative infinity, but at the end it's infinite value. If this limit has b and m of the same values, so the limit itself will be just the coefficient in the numerator divided by the coefficient in the denominator, which is a over b. The last the last option, the denominator power will be greater than the numerator power, which means m is greater than p or p less than m, and at this case, this limit will approach 0. Also, one of the definition, which is very helpful and makes some confusion for many people, if we have limit n approaching infinity of 1 plus x over n all to the power n. If we are trying to substitute this using the regular substitution, 1 plus some number over n, which n approaching infinity will give us 0. So it will be ending as 1 to the power of infinity. And if this happens, this is one of the quantities that we need to use something like L'Hopital rule or redescribing this function using logarithmic substitution. So after doing this logarithmic substitution and move through L'Hopital, this will end up as e power x. So simply, if we can see something like this is just the definition of e power x. If this x here is a positive number, so it will be e power x. If this x is multiplied by a negative number, so this will be e power negative x. So again, this plus an x will move to the exponent power by the same sign. Also, something from the geometric sequence or the geometric series, if we have any number to the power n, and then this number is less than 1, like half power n, when n approaching infinity, this limit will be 0. And if this are greater than or equal 1, so we are talking about this number to the power infinity, and then this limit will be infinity. So this will be helpful if we have just some number to the power n. Also, some kind of properties of the limit, if we have plus or minus, or if we have product, so we can distribute the limit among these like mathematical operations. So the limit of the product or the limit of addition or subtraction of two terms or more, it will be the addition or subtraction or even the product of the limits of each term of these terms. Something also finally to remind ourselves with, if we ended up in the limit to have 0 over 0 or infinity over infinity, don't forget, we need in this case to use L'Hopital. And L'Hopital, it has nothing to do with the limit, we just simplify the limit to be, instead of numerator over denominator giving us this problem, we will take the limit of the derivative of the numerator divided by the derivative of the denominator, and we can repeat this process many times until we got some value rather than 0 over 0 or infinity over infinity. So if we have this kind of undefined quantities. So let's return back to our question. First question was an, which is the nth term or general term of the sequence, an equal n plus 2 over n squared minus 3. So the only test we have right now, just I will take the limit when n approaching infinity of this len, n plus 2 divided by n squared minus 3. If we are trying to substitute with infinity, it will give us infinity over infinity inside the len. So just to remind ourselves, I can leave this len out, and I will take the limit of n plus 2 over n squared minus 3 with n approaching infinity. All of this inside the len. Using the properties we already talked about previously, if we have polynomial over polynomial, if we have the numerator degree or the numerator power, greatest power here, less than the denominator greatest power, so this means this one will be 0, so this will be len 0. Len 0 approaching negative infinity. So this means this term right here will approach negative infinity at the end of these terms, which make us like pretty sure about this sequence as divergent sequence. So this is what we mean about getting the sequence. The second one, which 2 power n plus 3 power n divided by 4 power n, again, if I need to take this test here, so it will be the limit problem. when n approaching infinity, 2 power n plus 3 power n divided by 4 power n. As also we did in some tips about the limits in the previous slide, each one of them, it's a number greater than 1 would give us infinity, so this will be infinity over infinity. We don't need to use L'Hopital in this case. This is one of the special cases that can be, like, we can deal with, like, with something very simple compared to L'Hopital, which I need at the end some zeros. So I'm just trying to get some zeros inside this fraction or this quotient function. How can we do this? How already, like, we deal with something like this? If we need to get some fraction to give us 0, we need the fraction to be less than 1 to the power n, and then when n approaching infinity, this fraction will give 0. To already transform this whole fraction into some fractions less than 1, it means I need to divide by the greatest number here. The greatest number here is 4, which is in the denominator. So we can just divide here by 4 power n in both sides, numerator and denominator, and then the new limit, when n approaching infinity, it will be 2 over 4 power n plus 3 over 4 power n divided 1, which is 4 over n divided 4 power n. Each one of them, 2 over 4 less than 1. 3 over 4, of course, also less than 1. So this means in the limits properties, this will give us 0 plus 0. So this will be 0. Again, this value is not equal to infinity. So this means this sequence converges to 0 at the end, which a value rather than infinity. So we call this sequence as a convergent sequence. So again, it's just a limit problem, and then we can solve the limit problem using whatever method we like, or the easiest method we can see can resolve this problem. Let's see something else. Again, this is the nth term or general term. Just taking the limit here, limit n approaching infinity of 1 minus 2 over n whole to the power n. This is, again, will remind us with the exponential formula. Again, e power x, it's the limit n approaching infinity, 1 plus x over n whole to the power n. It's the same, but here's a number again. This is 2 as the sign is negative. So this is simply, without doing any more steps, this is e power negative 2. E power negative 2, which means this one over e squared. So this one over 2.7. Any numbers, you can calculate this using your calculator. Squared, again, it's a number, not infinite. So it means the sequence will be convergent with this value. So we call the sequence as a convergent sequence. Okay, let's move forward to the infinite series. So the infinite series, it's nothing but the sum of the sequence terms, which we already discussed before. So if we have, again, any kind of sequence, for example, this 1 over n, which the terms here in the sequence will be 1/2, 1/3, up to 1 over infinity, which is 0. And we discuss how to test any kind of these sequences using the limit test. The series will be the sum of these whole numbers. So we need to add all these terms together and then figure out what the value of the sequence of this series will be. So again, the requirement for this infinite series to be tested, if it will, this sum will be convergent, so this sum will give us some value, or this summation will approach plus or minus infinity. If we have any of these cases, this is what we already tested the series. So we have there are many tests, but we will focus here on 5 tests. The first one, which is called the divergence or the nth term test. And this test states if the limit of an when n approaching infinity, if this test will give us some values rather than 0, so this will be conclusive to give us some information about the series, that the series is divergent. If this limit give us 0, so it's inconclusive. So I can't determine anything. I can't tell anything. I have to use another test. The second test, so this is the first. The second test, it will be the integral test. The integral test, if we do summation for like infinite terms, this can be approximated by the integral itself, and the integral will be slightly or some value which may be greater, slight bit more than like slight greater than the series itself. So we just can do the integration, and if this integration gave us some value which is not infinite, we call this series again it's convergent. If this integration gave us infinity, we call this series is a divergent. For sure, we have to determine which tests should be used at the beginning. The first one, it's general. I mean general, like we can try it by inspection, just to get the limit. If this limit give us some value, so okay, the series is divergent. If not, we can see if the integral test can solve this one or no. So the integral test can be used if an is integrable, like something can be integrated easily, and this depending on the form of this an. The third and the fourth test, which is the ratio test and the root test, there can be used in some specific cases. For example, this ratio test, if we have any number r power n, plus we have some factorials. If we have factorials and we have number power n, so here, in this case, we can use this ratio test. What's this ratio test? It's just the limit when n approaching infinity, an plus 1, which is the term of at n plus 1, divided by the nth term, which is an, and taking the absolute value, just ignoring any positive, any negative quantities, and then at like any other limit. This limit can be less than 1, which means an plus 1 will be less than an, which means also this series will be decreasing. So this one is called convergent. If an plus 1 greater than an at infinity, so this means this limit will give us some value greater than 1, so this series will be divergent. If the limit exactly equal 1, so right now it's inconclusive and I can't tell using this test. The last one, which is the root test in this force, the root test can be used if we have any function, and then this function, it's a function to the power of n. So simply the first, second, and third will not be applicable and are not easy to be used. So this one will be here. It's a suitable test for this kind of problems. So we just talk here the root of the an itself. So if it's a function to the power n, the nth root will cancel this power, and then we'll take a problem limit n approaching infinity. And also this will give three conditions. If it's less than 1, as we did in the ratio test, will be convergent. Greater than 1 will be divergent. If it's already exactly equal to 1, so this again it's inconclusive, which means again we need to use another test. The last one in these tests for us, which is a comparison test, or we can call it sometimes a limit comparison. Both are related to each other, but we focus today on the limit comparison test. Before going through this limit comparison test, for its name, we are comparing our an, which is a known series that to be tested, with some series which should be already like well known if it's convergent or divergent. Most of the time we are comparing with what we call P series. P series, it's nothing but 1 over n power p. For example, we can see 1 over n cubed. We can see 1 over n power 5 over 2. Or we can get 1 over n, or 1 over a square root of n, or 1 over n to the power 1 over 3. All these cases is called P-series. Without any proof right now, there's proof already from using the integral test, but it's not required right now. It's just we use this as a given. So if P is greater than 1, which is the power of this n, this P-series will be convergent. If it's the opposite way, if P less than or equal to 1, so this series will be divergent. So for example, 1 over n cubed is a convergent series. 1 over n to the power 2.5, which is 5 over 2, it will be convergent series. 1 over n divergent, 1 over square root of n divergent, 1 over cubic root of n divergent. Return back to our test. So we are comparing with P series. P series here, which is 1 over n power p. Where is this p? P is just the difference between the power of the denominator minus the power in the numerator. So if we have any polynomial multiplied or product with another function in numerator or even denominator, we're just interested in n itself. If we have terms n power something in both numerator and denominator, just we will get the power of the denominator minus the power of the numerator. We are speaking about the greatest power in both sides. So then we will get p, and then we can determine if this p is greater than 1, this would be convergent. We are comparing with a convergent series. If p is this one less than or equal 1, this will be compared with a divergent series. The limit comparison test states if we are taking the limit of n approaching infinity, our an, which is to be tested, divided by b of n, which already well known, and then this test it's not equal to 0, then whatever bn is, an will be. So whatever, if bn convergent, an will be convergent. If bn is divergent, it will be divergent. A trick, we already can understand this since the beginning. If the difference between the powers of the denominator and the numerator greater than 1, so our series will be convergent. If the difference in the power between the denominator and the numerator equal or less than 1, then our series will be divergent. So what happened in all the previous slides, we are assuming our series are all positive numbers, the same sign. What happens if we have alternating series? Alternating series, it means as a formula, we will have this negative 1 power n multiplied by the nth term or negative 1 power n plus 1. If we have something like the first or the second form, then our terms will be positive one time, negative, and then going positive and then negative, which we call as alternating series. Some hint, if we know something about the positive or the absolute value series, then we can use this hint. What about the positive series? If we have some information about sigma an, we already tested this before, then the new one here will be very easy. So first we need to already test sigma an. If this sigma an, which all positive terms convergent, it means that the sum of all terms will give us some value. If I give you some values, all added together will give you a constant, then if we subtracted some values from this whole summation, for sure this will be also giving us some value, which less than the previous value. So then, if it's already convergent, the alternating series will be also convergent, and we call this case here, it's absolutely convergent. What I mean by absolutely convergent, it's in any case, if it's all positive or even some of them positive and the other are negative, in both cases it's convergent, so it's the absolutely convergent case. In the other side, if our series is divergent, it means the sum of all terms inside the series will will result in infinite value. Then if we subtract some values, there is some kind of trick here. Maybe after subtracting some values, this infinite value will give us something less than infinite. So the series will return back as a convergent series, or the series will return back as just subtracting some few terms will again bring out an infinity again. So we need to check. What kind of a check we need? It's already divergent at the beginning. We check both conditions. What these conditions? If the last term in this series, which is the first series, this last term approaching zero, and the second term, this series also is a decreasing series, means an plus 1 is less than an, then under this condition, which is alternating, this series will be convergent. So we call this as a conditionally convergent series. If one from this one here, if one or two conditions are not satisfied, so the series will remain as a divergent series. So the condition here, number one and number two, must be satisfied. And in this case, our positive series, which already was before a divergent one, it will be conditionally convergent. If one of these two conditions, or for sure both of them, are not satisfied, then our series will remain divergent. So this is how we already test this kind of alternating series. Let's try to test the following series. We have multiple of examples, and please focus with me here to move through them very quickly. So an here is given as n over n plus 2 for the first example here. So to test this one, since the beginning, the easiest one is the first test, which is the nth term or the divergence test. We can just take the limit when n approaching infinity of the nth term, which is n over n plus 2. It's a polynomial over polynomial, the same powers in both terms, so it will be the coefficient of n in the numerator divided by the coefficient of n in the denominator, which is 1 over 1. Again, this value is 1, not equal to 0, so for sure this series is divergent. Something else, series of cosine n starting from n equal to 1 up to infinity. Again, no problem to try the nth term. So limit when n approaching infinity of cosine n, it will be cosine infinity. Again, this cosine infinity, it's some value. I don't know this value, but this value for sure it's something between -1 and 1. So if it already has a value, but this value is not well known, but again, it's not 0 all the time, so it means this series again is a divergent series. Or this is the first two examples here using the divergent test. The third one, it's sigma n equal to 1 up to infinity, 2 power n plus 3 power n divided by 10 power n plus over 2. Again, we did something close to this in the sequence test, and we already understand if we have limit when n approaching infinity of r power n, and this r less than 1, it's a fraction, this limit will approaching 0. Sorry. So this is the case again. So how to do this for the next second time? This term I need just to rewrite as 2 power n, and then 3 power n, 10 power n over 2, it's 10 power half, all to the power n, which means root 10 to the power n, root 10 to the power n. So this one root 10 to the power of n. Root 10 for sure, 3 and 2, the squaring of these numbers is 4 and 9. So root 10 for sure it's greater than 2 and greater than 3. It's 3 point something. What I'm asking about this thing right now, because we need this here to make sure if we are taking the limit when n approaching infinity, dividing by the greatest number. So the greatest number in this case will be 2 over square root of 10 all to the power n plus 3 over square root of 10 to the power n. And then we'll get surprised. This limit when this fraction less than 1 will give us 0 plus 0. So this one will be 0. So it's n conclusive, which means I can tell using the divergence test. Okay, what will happen if this one won't help us in this case? If this is not helpful, there is something else. If we already encountered some problem, includes number to n, to the power of n, using the ratio test. So I will use here, using the ratio test. Let's say, so limit when n approaching infinity, here I will an plus 1, which 2n plus 1 plus 3 power n plus 1, divided square root of 10 to the power of n plus 1, divided by an, which is multiplied by the reciprocal, so root 10 over n, divided by 2 power n plus 3 power n. This one will be cancelled with one n here, so we'll end up limit when n approaching infinity, 2 power n plus 1 plus 3 power n plus 1, divided by 2 power n plus 3 power n, and then we have 1 over square root of 10 here. The same thing, if we ending up trying to solve this limit, then we need to divide by the greatest number here. What's the greatest number? We have 2 and 3, so the easiest way here to divide by 3 power n. So then here we'll end up limit n approaching to infinity. It will be 2 over 3 this power n, and dividing this by 3 power n, it will end up with 3, 2 over 3 power n. This is here plus 1, and also here there is 2 outside. And we have 1 over root 10, don't forget this term. We need every constant to be considered carefully. So when n approaching infinity, every fraction less than 1 will give you 0. So this is 0 and this is 0. So it means we will end up 3 over square root of 10. Don't forget, square root of 10 is greater than 3. So this fraction will be less than 1. So my series here will be convergent. So this whole term 0, this whole term 0 will end up just 3 over 1. What we did, we just divided by 3 power n both terms, numerator and denominator, both sides, sorry. So again, let's move forward. So number 4, len n squared divided by square root of n. Again, we don't know something specific for this one, so the general test, which is the divergence test, which is limit when n approaching infinity, len n, this is squared over square root of n. This will give us infinity over infinity, so I can apply L'Hopital. So it will be limit when n approaches infinity, 2, and then multiplied by len n power of 1, divided by 1 over n, the square root of n here, the derivative 1 over 2 square root of n. Just reform this fraction this will be 4, and then square root of n go up, so you'll end up with ln n over square root of n. Again, this will give us infinity over infinity. So again, L'Hopital for the second time, limit n approaching infinity, 1 over n, and then the denominator 1 over 2 square root of n, and this is 4. This will be 8, and then this 1 over square root of n. This limit when n approaching infinity, this will give us 0. So the test here is inconclusive. So we have to figure out something else. In this case, just this here, this is very simple. The ratio test will not be helpful. For sure won't be helpful. This is nothing related to n factorial or even number to the power n. But what we can consider here is the limit comparison. So compare which terms with which terms. Assuming there is no n in the numerator, we have n to the power half in the denominator. So I will use limit comparison with gn equal 1 over n to the power p, and p equals half minus 0, which is the difference in powers between the denominator and the numerator, so it's half. This half here is less than 1, so I'm comparing with the divergence series. So what should we do? Just limit n approaching infinity. My an, which is ln n squared, divided by square root of n, divided by bn, sorry, which it's divided by 1 over square root of n, so it's square root of n over 1. Just this square root of n will cancel with this one. You'll end up with limit n approaching infinity of ln n all squared, and then this at infinity will be infinity squared, which is infinity. Again, this is not equal to 0, so I'm comparing a series with a divergent series. So my series under test right now, it's a divergent series as well. So what was helpful here, this is a limit comparison test. What about this small one? It looks trivial. Yes, assuming e and pi any kind of numbers. So don't forget, it's the p series, and just add all these powers to be in the denominator, to be in the standard form. So 1 over n pi minus e. Pi is 3.14 as approximation, e is 2.7 as also approximation. So the difference between them is less than 1. So pi minus e is less than 1. What this means? It means it's a p series, and b series has value less than 1, so it's a divergent series. So from the definition, 1 over n power p, this is my series, and this p less than 1, so we are already considering a regular p series, a standard form, and b less than 1, so this one is a divergent series. Number 6, we have 2n over n power 4 plus 1. Again, if we have polynomial over polynomial, so don't think about anything rather than the limit comparison test. So here I need to compare this. I will use the limit comparison with bn equal p series 1 over n power p, and b as 4 minus 1, which is the difference between the powers. Again, denominator minus numerator. So this will be 3 greater than 1, which I'm comparing with 1 over n cubed. Let's do this limit comparison. Limit when n approaching infinity to n divided by n bar 4 plus 1, multiplied by the reciprocal of bn, which is n cubed over 1. Again, if you compare this correctly, you will figure out the powers of the numerator. It's the same as the power of the denominator because we multiplied by the difference. So it will be the coefficient over the coefficient, which is 2. This one not equal to 0. So it means I'm comparing with a convergence series. So my series will be convergent. Let's see number 7. Again, it's 1 over n squared minus n multiplied by sine n. I don't know what to do here, but again, I can use the limit comparison with the series. And IB is the difference between the greatest power in the denominator minus the numerator, which is 2. So this one greater than 1, which is convergence series. So my Bn is 1 over n squared. Try to get the limit, n approaching infinity. An, which is n squared minus n sine n, divided by Bn, again, the reciprocal. So to get this idea here and try to get this limit, the easiest way, if it's not assuming this polynomial and this gives some confusion for some of you, this will be limit n approaching infinity. I'll divide by n squared everywhere, so this will be 1 minus sine n over n. At infinity, this term is some number. Divided by infinity, this will be 0. So again, this will be, again, not as we already predicted at the beginning, the numerator is the coefficient of divided by the denominator coefficient, which is 1. This value is equal to 0. Then I'm comparing this convergent series, so my series will be convergent. Number 8, we have 1 over ln square n. We're starting from 2 to infinity. I think this is something maybe helpful to remind ourselves this comparable to 1 over x ln square x, which related to the integration. So I think this will be helpful if we are using the integral test. So I'm just doing the integral from 2 to infinity, 1 over n, ln squared n g, and so the derivative of ln g, which will be n over n, and this is ln power negative 2. It's as if 1 over u squared du, it will be negative 1 over ln n. And substitute with 2 and infinity, don't forget. This will be the negative sign. I can cancel this negative sign, and substituting with the lower limit minus the upper limit, it would be 1 minus ln 2 minus 1 ln infinity. Ln in infinity is infinity, so this will be 1 over infinity is 0, and 1 over ln 2 is just a value. I don't need the exact value. Again, this integral is not equal to infinity, so my series right now is convergent. Let's move to the next one, number 9. It's ln n over n. Again, this looks very interesting. We use the integral. So again, this as we did previously, using the integral test, integration from 1 to infinity, ln n over n dn, du times u, so this ln n to be ln n squared over 2, substituting with infinity and 1 will be ln infinity squared minus ln 1 squared divided 2. Ln 1 is 0, ln infinity is infinity, then this be infinity over 2, which is again infinity. The integral will give us infinity, so this series is a divergent series. Okay, number 10. We have the sigma from n equal to 1 up to infinity, 10 power n over n factorial. Okay, the factorial is here, so easily we can use the ratio first. The ratio was limit n approaching infinity, an plus 1, which is 10 power n plus 1, with n plus 1 factorial, divided by an, which is the reciprocal of this one. This factorial is cancelled, this factorial will end up just n plus 1. 10 power n will cancel, 10 power n will end up with 10. So this limit n approaching infinity, 10, divided by n plus 1. At infinity, this 10 over infinity is 0. In this test, we are comparing with 1, so that's less than 1. So then, our series under test here is a convergence series. Let's move to the number 11, which again, all factorials, so looks like nothing will be helpful but the ratio test. Limit n approaching infinity, 2 power 3n plus 3. Don't forget an plus 1, so substitute each n with n plus 1. So it will be 3n plus 3. And we have n plus 1 factorial or cubed divided by 3n plus 3 as a factorial. And then this 1 multiplied by the reciprocal, which is 3n cubed, divided by 2 power 3 power 3n, and n cubed, n factorial cubed. Just cancel the similar terms. This will be cancelled with this one. So it'll end up as 2 power 3. And 3n plus 3 here, we will end up 3n plus 3, 3n plus 2, 3n plus 1, and the factorial will cancel those as factorial. N plus 1 factorial all cubed will have n plus 1 3 times. So again, it's easy. It's a polynomial over polynomial from the third degree in the numerator and the third degree in the denominator. So it will be the coefficient divided by the coefficient. So this one will be 8 times 1, which is the coefficient of n cubed. N cubed from the denominator, it will be 3 times 3 times 3. So it's 8 over 27. Again, it's a fraction less than 1. In the ratio test, comparing with 1 if the value is less than 1, so this series is a convergence. Okay, let's move to 12. Again, factorial and n power n. Again, this looks a ratio test. Let's see. So this limit when n approaching infinity, n plus 1 is factorial by n plus 1 to the power n plus 1. Again, multiplied by the reciprocal, which means I'm dividing by an, which n power n, divided by n factorial. This will be cancelled with this, ending up as n plus 1. This n plus 1 will be cancelled with this one. Will end up with limit n approaching infinity, n power n, divided by n plus 1 to the power n. Don't be confused, this can be rewritten as 1 over n plus 1 over n all to the power n, which again, this limit will be n approaching infinity, 1 over 1 plus 1 over n all to the power n. This is again the definition of the exponential function, which 1 over this is e power 1. So this 1 over 2.7, which a number less than 1. So it means my series here is a convergence series. Okay. Let's move to number 13. We have a function and then this function to the power of n. So the ratio test will not be that helpful. Let's try the root test. So using the root test, limit when n approaching infinity, the square root of n, whole function to the power n which is 2n squared minus 1, n squared plus 3. The root will cancel the power, which will end up with a simple limit when n approaching infinity of 2n squared minus 1 divided by n squared plus 3. The same order or the same degree of both polynomials in numerator and denominator be the coefficient over the coefficient. This 2 is greater than 1. So root test or ratio test, if we are comparing with 1 and the value is greater, so it means my series right now is a divergent series. And in number 14, we have many functions to the power of n, so you will be sure to use the root test. So my root test is limit n approaching infinity, the nth root of an itself, so we'll cancel all the n's power. So limit n approaching infinity, len of 1 plus len n divided by len n. There is no properties of the product or the division of logarithmic function together. So here, if we have something like this, let's remind ourselves there is actually a rule. If we have len divided, but inside it will be the subtraction between len A and len B. So you don't get confused with the rules if the division inside the len or the division between two lens. There is nothing between two lens to be simplified. So let's move forward. I need to get this limit. This will be limit 1 plus infinity. It will be len infinity. Len infinity in the denominator, which is infinity over infinity, which is a simple definition to use L'Hopital. Trying to use L'Hopital, limit n approaching infinity. I'm applying L'Hopital here. So when we applying L'Hopital, here I have len n and the denominator will be 1 over n. In the numerator 1 over 1 plus len n multiplied by 1 over n, which is the derivative of whatever inside the len in the numerator. This will cancel this one, and you will end up with 1 over 1 plus len n. Again, we will have here limit n approaching infinity, 1 over 1 plus len n. Right here, it will be 1 plus infinity, which is 1 over infinity give us 0. Again, in the root test, we are comparing with 1, so this is less than 1. So it means this series is a convergent series. So this is the case here. Move to number 15. So number 15 is basically alternating series. So before going into this test, I have to consider the positive series, which is n equal to 1 to infinity, 1 over n plus 3. Again, you can use your knowledge from the 14 examples we did before, and then you can figure out this using the limit comparison test with Bn. It's 1 over the square root of n, which is divergent. You can solve this by yourself, and then you will figure out this series is divergent. If it's divergent, we have two conditions. The first condition, we need to get the limit when n approaching infinity of the positive series and check the value of this limit, which 1 over infinity will be 0. So this is satisfied. Second condition, I will get an plus 1, which is 1 over the square root of n plus 4. And an compared with 1 over the square n plus square root of n plus 3. Again, we understand. Let's put it here in another color. N plus 4 is greater than n plus 3. It means 1 over n plus 4 less than 1 over n plus 3. It means 1 over square root of n plus 4 less than 1 over square root n plus 3. If this already satisfied, so this means it's a decreasing an plus 1 less than an. Both conditions are satisfied, so my series right now is called conditionally convergent, which means it's already convergent when it's alternating. If we return back this series to be all positive terms, this series will return back to be a divergent series. What about this one? Again, to test this one in the positive series first, we did this multiple times. Limit n approaching infinity, n minus 1 over n to the power n. We'll figure out this one will be e power negative 1, which doesn't equal to 0. So this is not equal to 0. And then using the divergence test, give this series is divergent. Don't forget, if series is divergent, you have to move through the two conditions, but actually I don't need to move through the second condition because my test I already used at the beginning, it was the same, limit n approaching infinity of an, and this limit gave me e power minus 1. So the series divergent in the positive values, and if it's alternating terms already included, also remain divergent. So this is always divergent series. About this case, we have n squared over n power 4 plus 1. Again, if we need to test n squared over n power 4 plus 1, I think we already clever to use the limit comparison test here, or you may also use the integral test, whatever you like, comparing this with 1 over n squared, which 2 greater than 1, which is a convergent series, will end up, you can figure this by yourself, is a convergent, and then I don't need to do any tests. Why? Because if the series in the positive terms is convergent, means all the alternating terms will give us also convergent terms, which we call this kind of series as absolutely convergent. So no more tests? Yes, no more tests. Okay, the last one, hopefully. Number 18, we have this kind of series. So first, we need to figure out test the series. This series, it's 2 over 1 over n. This is the nth root of 2. So, okay, how can we test something like this? Let's think about something very easy. What about the divergence test at the beginning, which is limit n approaching infinity, this 2 over 1 over n, and see how this looks like. This will be very simple. It looks complicated, but it's not. 2 power 1 over infinity, which is 2 power 0, will give us 1. The divergence test states if the limit will give us something not 0, so the series will be divergent. Okay, the series will be divergent. In the positive terms, what about the alternating? You have to go through step number 1, the condition number 1, and condition number 2, and check their satisfaction. Okay, I don't need to go through this one or even this one. Why? Because here, the limit or the divergence test itself, it's already the condition number 1. So the condition number 1 is not satisfied. So the limit itself is not equal to 0. So the series in the positive terms is divergent, and in the alternating shape also it will be divergent. So hopefully we went through many examples that make good illustration for what we mean by sequence and series and their tests, and hope you'll find it interesting. And if you have any question, don't forget to ask very loudly. And thanks for considering listening to this video, and wish you all the best.